Hello everyone and welcome to We Meet at Digital Days. My name is Marie-Therese Kohl and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is how to select the suitable SMT ferrites, material, behavior, and key parameters. Simulation with RedExpert providing a new dimension for selection. Before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentations. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. You will find the chat function in the control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email afterwards. If you still have any questions left, just mail us at exhibitions@we-online.com. We will try to answer them promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our event. You will receive the link to the presentation in the next few days. Also, the recording will be available at our website. But now I will hand over to our speaker, Igor Rodriguez, and I wish you an exciting presentation.
Oh, now I'm unmuted. Good afternoon or good morning, everyone. It's a pleasure being here with you. My name is Igor, and I'm Field Applications Engineer for Würth Elektronik in the UK. And it's a pleasure being with all of you today here to discuss a little bit about the SMT Ferrite selection. So during this presentation, we'll be basically discussing some basics about the SMT Ferrites, and we'll try to understand the parameters to do a proper and good selection of these ferrites. And at the end, we will be visiting all the SMT Ferrite solutions that Würth Elektronik has got for you. And also, we'll be doing a little bit of a simulation and selection of parts utilizing RedExpert. So first of all, let's see some basics about the ferrites. And the first question that everybody will do would be, what is actually an SMT ferrite? And an SMT ferrite basically is the ferrite itself is a filtering component. It's a component that has got basically a wire, or if you want to call it a trace, that is inside a ferromagnetic core. Okay.
Igor, sorry for interrupting,
yes.
but I don't think that we see your screen at the moment. Maybe we can hand over the moderation control again.
I don't know what's
now it's
something.
working.
Sorry.
Perfect.
Oh, okay. So
No
apologies, everyone. So just, well, you actually, in terms of image content, you didn't miss too much, since this is our first content slide. But just recapping once again, the ferrite is basically a winding that you can hopefully see now on the screen that is inside a ferromagnetic core. And the reason why we call them SMT is simply because they are surface mount technology. As you can see here, they haven't got any leads, so you can utilize automated process such as a pick and place machine, flow oven, in order to get them soldered to your PCB. And there is even a little video here that shows a 3D CT scan of a ferrite, where we can dive deeper and see all the layers, all the trace, which is this yellowish part here, and the more reddish part is the core material. And you can navigate through the layers and see them like horizontally now. So basically, this is what you get inside this little guys, the SMT Ferrite. So it's a multi-layer structure, and these ferrites, they are done, they are produced by a method that looks like a giant printer that will deposit all the respective materials that we utilize. Okay, so moving ahead. Second question would be, what does it do? What is the role of ferrite? In general, ferrites are low-pass filters. So this means that they will block high frequencies and they will let the lower frequencies to pass. They will attenuate the higher frequencies. SMT ferrites are utilized as differential mode noise filters. And when do I use the SMT ferrites? Basically, whenever you have noise and you have to reduce, you have to attenuate this noise. So as you can see here, sorry that I pressed the wrong key. Basically, you've got the plot of the frequency spectrum, okay? And we have some peaks that we can spot that they are overshooting this red step line here. And this means that these peaks, they are frequencies where I have noise above the maximum limit that I can have in order to pass the MC tests and get my certification for my device. And also to ensure the good functioning of this device. So with the SMT Ferrite, what I'll do is that I will lower these frequencies, and then I will have my equipment working correctly and following all the standards and norms that do exist in order to pass on EMC. Basically, in order to understand how a ferrite works, we'll have to revisit some of the basic concepts involving magnetic field. And this is what we are going to be doing on the next slides. First of all, you can visualize here on this little video is that once you have a current flowing through a conductor, it will generate a magnetic field. And this is very important for the functioning of your ferrite. Basically, the ferrite will work by utilizing the resistive losses that it will create in order to convert your noise, which is electrical current at the end of the day, into heat. So you have electrical current that will generate a magnetic field. The ferrite will absorb that and turn it into heat. This is also known as impedance. So up next, we'll be seeing the concepts of magnetic field intensity, flux, permeability, and also magnetostriction that will help us understand a little bit better how the ferrites will work. So just a quick reminder here of your world famous right-hand rule. I don't know if you all know or remember about this, but basically, whenever you have a current flowing through a conductor, it will generate a radial magnetic field. Okay, so the right-hand rule basically consists on using your thumb on the direction of the current, and then your other fingers, they will form the magnetic field lines. Okay, so we can visualize this if we, for example, put some metal filings on a smooth surface, and we run a wire, a conductor, across the surface, and we flow some current through it. So you can actually visualize these particles of metal rearranging themselves on the shapes of the magnetic field lines. It's very interesting. And talking about the magnetic field lines and intensity, here you've got your ferrite that has got a wire going across it, going inside it. and you've got your current here. So basically we are in a situation where we've got magnetic field present here. So this magnetic field is going to be actually the same on the air or on your ferrite material. Okay, this is a little bit counterintuitive to some people, but actually it's the same. What is going to be different is that what we call B, which is the magnetic flux density, is going to be different. So it's going to be higher on your ferrite material. In the air, the magnetic field acts like if there was nothing. And the same applies if you put a piece of plastic or a piece of ceramic there. Your magnetic field will be like, oh, there's nothing interesting for me here. So it will just go from the point A to the point B, from the north to the south poles of your magnet that was formed there, like if there was nothing. But when you utilize a ferrite, look what happens. The magnetic field lines will be more attracted towards this material, because this material will form an easier path for the magnetic field lines. And in nature, everything is like that. Everything wants to go through the easiest path. So this is what we define as the magnetic permeability, or better saying, the relative magnetic permeability. So it's relative because we always refer to the air or to the vacuum. And then you have got this little number here that's called mu r, r of relative, and mu is the letter, the Greek letter that we use to define the permeability. And what happens is that in the air, mu r will be 1, because you've got the air itself, so you're comparing air to air, so it is 1, and it's a linear function, it will be constant. Nevertheless, when you analyze the mu values for a ferrite, you will realize that this relative permeability is not going to be constant. Instead of that, it will be dependent on various factors, such as the material, the frequency, the temperature, and also the current. Didn't mention here, but also the pressure can affect that. So mu r is actually a function, it's a variable value. So this is the definition itself of magnetic permeability. It describes the ability to concentrate magnetic flux inside a core material. And this, of course, will define how much energy that material needs for magnetization and how much energy that material can, for example, store in the case that you are talking about, for example, a power inductor. And basically, when you see what's inside a ferrite, you will see that inside the ferrite, we have what we call the magnetic domains, or you can interpret this as micromagnets that you've got inside your ferrite. And they are unsorted, which is good, because once you expose this material to a magnetic field, what's going to happen is that the magnetic field will sort these micromagnets. Okay. This kind of material that we utilize for ferrites, it is called soft magnetic material, right? Once the magnetic field goes away, the micromagnets will become unsorted again. Meanwhile, when you grab your typical fridge magnet, it is a hard magnetic material because they're always sorted. So this is not going to have any effect to what we want. We want to utilize soft magnetic materials on ferrites. And the magnetic permeability will depend, as we saw on the previous slide, on the material as well. So as you can see here, These are the three most common materials that we have to that we utilize in order to make ferrites. Iron powder and superflux, as you can see, you have between 50 and 150 of the value of mu r. It hasn't got any unit, by the way. Nickel zinc can give you between 40 and 1500. Meanwhile, manganese zinc can give you between 30 and 20,000. Another effect that we've got when dealing with ferromagnetic materials is magnetostriction. And you can see on this little animation here that we've got our magnetic domains that are exposed to a magnetic field, and they keep on flipping to one side, from one side to the other. This is a physical thing that is happening inside that material. And as there are forces that each of these magnets will exert on each other, you will have actually the material expanding and contracting. So it will change the shape and size of that material, even if it's at a microscopic level. And this will cause losses. This will convert electromagnetic fields into heat, because you're going to have there both friction and torque. So, and this is actually good. This is how ferrite works. In other words, it converts electromagnetic fields into heat. Okay, so we finished with the basics. So now another question: what ferrite should I select? Because there are so many. In order to select the perfect ferrite for you, you have to understand the basic parameters of the ferrite, and this is what we're going to do. The first one you can see already on your screen is the impedance curve. On every data sheet of ferrites, you will see a curve that looks more or less like this, perhaps not colored because we just colored it to give you a little bit of a better understanding. We have here three different colors, and each of these colors will represent one section of the impedance curve. The impedance curve overall will tell you how much impedance you're going to have on each frequency of the spectrum. Okay, and the first block, the blue one, indicates an inductive behavior, because as you can see, the impedance is growing with the growth of frequency. Then it comes the green block, that is a behavior that is more resistive, because your impedance here is changing way less with the frequency. It's changing a little bit, but it's changing way less. So your resistive behavior is prevailing over the inductive and the capacitive. And at the peak here, you can see what we call SRF, or self-resonant frequency. This is the point where the ferrite will be purely resistive. This means that the capacitance and the inductance that it has got will be the same. And yes, many of you might ask, well, but I've seen the ferrites being represented as with the inductor symbol, which is this one over here, because mainly it's an inductive component. You have a coil that's inside a magnetic core, but also you will have parasitic capacitance. That's why the curve starts on the last bit of it, on the yellow bit, starts going down, and it starts behaving as a capacitor. Actually, for attenuation purposes, you could utilize this ferrite for any of these frequencies that you can see here in the screen, the specific one. Nevertheless, the ideal point, let's call it this way, to utilize the ferrite would be around its peak, where it shows more of a resistive behavior, simply because you will have more impedance at this point, but nothing stops me from utilizing it on other points as well. And a mistake that is very, very often seen is that people will select ferrites based only on this table that they see on the data sheets, where it will give you the value of impedance at a given frequency, in this case 100 megahertz, or the maximum or the maximum impedance of the ferrite. But as we've seen, this is just one point in a big curve. So this can lead you to a mistake, and not always a ferrite that shows you the highest attenuation at a point will be the ideal and the best choice for you. Instead of that, always remember to look at the curve. That's important. And always have a take a look at which are the frequencies that you're having problems with. So identify which are these frequencies and determine how much attenuation you need in dBs in order to enable you to select the best ferrite for your case. Another parameter that we've got for ferrites is going to be the rated current. And the definition is quite simple. This is just a current value that will give you a determinate temperature rise. So basically, you will have ohmic losses on your ferrite, and this will generate heat. And this heat will increase the temperature of your ferrite. We can see here that we've got two rated currents, one at 20 Kelvin, a delta T of 20 Kelvin, and another one at a delta T of 40 Kelvin, respectively 600 milliamps and 9.6 amps. So always when you're selecting your ferrite, pay attention to these parameters in order to select a ferrite that has got a rated current higher than what you're actually utilizing, higher than the average current that you will have flowing through that ferrite. This will be good not only because you will have less self-heating, but also it will give you more attenuation. And the reason why is because there is something called DC bias current on the ferrites. Whenever you have an average current flowing through the ferrite or a DC current, it will change its frequency response, and the effect can be quite dramatic. The reason why is because remember that we have our micromagnets inside a ferrite. We also call these Weiss domains. And what happens when you have a DC magnetic field applied here is that some of these domains will join together to form a bigger domain. So you will have actually less micromagnets available in your ferrite material in order to do the attenuation job, which is what we want. So it can reach to a point where you will have just a single domain or a few domains, and you will not have any attenuation at all. So this is another mistake that is frequently seen, and you can avoid it. Look at this example. With RedExpert, we can easily visualize this problem. I just grabbed a random ferrite here, and I started changing the bias current. First, without bias current, I measured the impedance of this ferrite at 300 megahertz, and I found that it had 120 ohms. Meanwhile, with 1 amp, the impedance at the very same frequency fell to 29.2. So it's quite a steep fall. So it's more than 4 times less. Then at 4 amps, look at that, it falls even more to 15, almost a half that we had at 1 amp. So we can utilize RedExpert to see these, and this is real data that we've got there in RedExpert, so you can trust on this. Okay, so we have various ferrite types. These are the 4 main types, and this is how we sort of divide our ferrites. So it's really common to see these nomenclatures when you are selecting the Würth Elektronik SMT Ferrites. First one is HC, or high current. High current is self-explanatory. These are ferrites designed for usage on power lines, so they can withstand a higher current. And nevertheless, everything has got a price. So if the current is higher, you will have thicker traces inside the very same space, so you have less material, thus, and less turns, thus you will have less attenuation. WB, or wide band, again, self-explanatory. It has a really wide band on the frequency response of the ferrite. So it will attenuate lower frequencies and higher frequencies as well. So a suggestion of usage is to suppress broadband noise. HF is high frequency. And with high frequency, we have a little definition that these ferrites will have approximately 3 times more impedance when compared to a regular ferrite at 1 gigahertz. So this can be quite useful whenever you have any application that is generating or suffering from high frequency noise. And last but not least, we have the high speed ferrites. They're not high speed because they're going to be like going on the road really, really fast. No. They are high speed because they are designed to be utilized with high speed signals. So your high speed signals will suffer less attenuation in case you're utilizing this on a data line. Meanwhile, the noises will have higher impedance waiting for them, so they will be more attenuated. Temperature is another parameter that we always have to be vigilant because essentially we have something that's called the Curie temperature that will affect the ferromagnetic materials. Curie temperature is a temperature to when this material reaches it, it will lose its magnetic properties temporarily. Once it cools down, it will start behaving as a ferromagnetic material once again. So this means that if you will reach this temperature, your device is not going to work anymore. Your ferrite will cease to work. So we have to be careful with this. And in order to know how hot your ferrite can get, you have to take in consideration the following. You have to take in consideration that your operational temperature will be the sum of your ambient temperature and the temperature rise that the self-heating of your ferrite will get you. So this sum must be always within the limit established on the data sheet. Size is another important consideration as well, because after all, if you're doing like a micro portable device, you're not going to want to have a big chunky ferrite inside of it. You're not going to be able to carry this weight and this volume around, so you'll opt for a smaller ferrite. On the other hand, you'll always have the compromises that, for example, if you need a high current application, you will need a bigger ferrite, or if you need a really high impedance, you will need a bigger ferrite. It's all linked to physics. And size-wise, we have our ferrites from the size 02, 01, so this is 0.6 per 0.3 per 0.3 millimeters. It's quite tiny. It's almost like a grain of sand. And the biggest size is 12 by 12 by 8 millimeters. So always bear that in mind to balance the real estate versus the functionality. And for special Inrush or applications that have got repetitive pulses, you can utilize WE-MPSB. This is a really special kind of ferrite that is unique in the industry, and it's got a special internal design that allows you to withstand these pulses without literally breaking the ferrite. And this ferrite is specified for pulses for Inrush current. So you have the specification on the data sheet, and you can visualize these as well on RedExpert, and we'll do this together later on this presentation. So it's got a ton of good features, such as a really low DC resistance and a good number in terms of impedance, and the DC bias behavior is minimized on this kind of ferrite. So once again, the most important thing of it is that it's peak current rated, so you can utilize it on these really difficult applications. Okay, and we have the calculator on RedExpert that we'll be utilizing. Just as a reference, they have up to 20 times higher peak current rating regarding the average current rating, okay? The rated current. All right, so moving forwards, now we'll take a quick look at our ferrite portfolio. So we divide this in two. So we have, first of all, the chip bit ferrites, and also we will have the wired ferrites. So on the chip bit side of things, we have TMSB, CBF, CBF high frequency, and MPSB. And basically TMSB are the tiniest ferrites that you can get, and they are wide band. Meanwhile, CBF are the bread and butter ones that you can have wide band, high speed or high current. Same for CBF HF, only difference is that it's high frequency. And MPSB is the special Inrush specified ferrite that we've just seen on the previous slide. On the wired ferrites, we have three different families. We have WE-PF, which has got the highest impedance of them all. We have WE-PBF, which is good for high currents, and it's good for inrush currents. And finally, WE-SU-KW, which is also for high currents, inrush applications, and the higher spectrum of conducted emissions or immunity. And here on this slide, you'll be able to have the presentation after this. I put together a little cheat sheet so you can go ahead and see the main points of each of these ferrites, and you can have an idea as well of their impedance ranges and also their current ranges. Okay, so let's go for the last bit of our presentation, which is RedExpert. And with RedExpert, you have a dedicated module for the SMT ferrites. All right, so this can help you selecting the ferrites quite easily. And I will show you a couple of examples here, and you will see how fast it is. Okay, so this will be our first example that we'll be doing live. So the case will be of a power line, a DC-DC converter of an automotive application that has got a spike at 200 megahertz that has to be attenuated by 25 dBs. And the average current flowing through the ferrite will be 2 amps, and we need the smallest possible solution. If you were to go ahead and start looking at data sheets and catalogs, you would take a huge amount of time until you would find the ideal component, if you would find actually the ideal component, because there are so many. But with RedExpert, which is the tool that you're seeing here, free to use, easy to use, you can do this in seconds. So this is the homepage of RedExpert. I left the link on the presentation for you. And if we click here on products and ferrites for PCB assembly, we will go to our PCB ferrites module. And here we have got a parametric search. We can see on the bottom of the screen they are loading the impedances and reactances, some curves of our ferrite that we were discussing a little time ago. And in order to do our example, we will utilize this tool here that's called System. I will click on it. And here I will be inserting my parameters. So I want 25 dBs. So let me type here 25. The frequency that I want is at 200 megahertz. And I specify the current of 2 amps, which I can select here, 2 amps. And also I mentioned that this was a DC-DC converter. If I don't know the exact impedance, which I can put here, the input and output impedance, I can use this slider. In this case, I will do that. So I'll put it here on supply voltage lines, VCC. And just a second. Oops, there was a little bug, and there we go. Okay, so basically, I said also that I want an automotive part. So I can come here on the automotive filter, click here, continue, and we're good to go. So I'm down to only 2 candidates, and I want the smallest one, so I can sort here by size. And off we go. This is the smallest solution for my issue. Okay, pretty easy and fast. All right, so we have other 2 quick examples. By the way, I have the link for the solution here, so you can see my very same screen. So the example 2 will be for pose applications that we've talked about. So on this example, we will do a single pose selection and an 8 millisecond pose repetition selection. These are the 2 tools that we've got available at RedExpert. So for single pose, the ferrite must withstand, in this example, 90 amps for 3 milliseconds of duration with an average current of 2 amps and an impedance of more than 50 ohms at 200 megahertz. This was all, of course, previously calculated. And also a maximum size of 5 by 5 by 4 millimeters. So I can easily come to here and I can continue with the selection by utilizing the pose tool. I can come here to pose and look how easy and fast it is. After you do this a couple of times, you will be like doing it really, really easily. So I can put here 90 amps for 3 milliseconds. And let's remove the automotive filter that we have here because this is not a requisite anymore. And let's edit this filter. I'll click on it because we need at 200 megahertz at least 50 ohms. Okay. And at last but not least, we will filter by size. So we have length, width, and height. So I will limit length on 5 millimeters. And you've selected your ferrite already. Okay. That easy, isn't it? Our last example will take just 1 more minute. We want on the example 2b, utilizing the 8 milliseconds pulse repetition tool, the ferrite will survive at least 50,000 pulses of 32 amps. So once again, it's really easy. Let me reset the module. Ready? And let's use the pulse tool again. So we want the pulse repetition for 8 milliseconds, 50,000 pulses. Sorry, I typed an extra 4 here. Of, let me remember here, of 32 amps. And after you enter the information, it will calculate automatically for you which ferrite can do the trick for you. And voila, your ferrite is selected. Okay, so this leads our presentation to an end. So now we have a space for your questions.
Yes, thank you, Igor, for your interesting presentation. As you already mentioned, now we would like to turn our attention to your questions and wait a little second until some questions have come in and everyone can enter their questions into the webinar control panel within the chat function. So Igor, let's have a look maybe on a first question. Igor, what is the difference between a signal power ferrite bead with the same values?
What's the difference between a signal
And
ferrite bead with this and
yeah, and power ferrite bead with same
and
value?
power? Yes.
Yeah.
Well, basically, the signal ferrite beads, they will have a lower rated current, first of all, and also the signal ferrite beads, or what we call the ferrites for signal lines, they will have less attenuation on the first part of the spectrum, on the lower frequencies, because your signal will be there. If it presents high attenuation on that frequency range, it will distort your signal. So your communication will not happen, or your bit error rate, for example, will be too high. And meanwhile, the power ferrite, the power line ferrite, it doesn't have really to care too much about it, because whenever you transmit power, you'll be transmitting power on lower frequencies, or DC in most cases, which is the frequency is zero, basically. So it can have really high attenuation also on the lower side of the spectrum.
Okay, thank you. And one more
You're welcome.
question. Can you use several ferrites in parallel to gain higher current rating?
Utilizing several ferrites in parallel to get more current,
Yeah.
it's not a common practice. It's not a common practice. Of course, the line of thought was really good, or whoever did this question. Thank you very much. Because of course, if you put several resistors in parallel, you're lowering your overall resistance. But the reaction on the impedance will not be of maintaining that impedance, so you'll have less impedance as well. Remember, when you mathematically model an impedance and you put them in parallel, you will have a drop of that impedance overall. So it's not going to be good. So perhaps it will give you, yes, more current capability, no doubt about that. But then you'll have to see what is going to make on the side of attenuation. Okay.
Okay, thanks, Igor. Because of the time, I would say if there are any questions left, we will answer them via email afterwards. But for now, we are finished with this presentation. Thank you very much, Igor, and thank you very much for your attention. And I hope you enjoyed our presentation. The next presentation topic is how to select the suitable EMC cable ferrite according to parameters and application. The presentation will start at 3 p.m. See you there and enjoy our digital days. Goodbye.